Nuclear power plants are absolute marvels of modern engineering. They harness the incredible energy locked inside atoms to generate a huge amount of electricity without producing the greenhouse gases that contribute to climate change. At the very core of these facilities is a process called nuclear fission, where atoms are split apart, releasing a tremendous amount of heat. This heat is the prize we're after, as it's used to boil water, create steam, and spin massive turbines to generate power for our homes and cities. It's a clean and powerful way to keep the lights on, but managing that intense heat is the most important job inside a nuclear power plant. Without constant, efficient cooling, the temperatures could rise to dangerous levels. Think of it like the engine in a car. Your car's engine gets incredibly hot as it burns fuel to move you forward, and it needs a radiator and coolant to stop it from overheating. A nuclear reactor is similar, but on a much grander scale. The heat generated is so immense that it requires a highly sophisticated and completely reliable cooling system. This system is not just about efficiency, it is the absolute cornerstone of the plant's safety. Its primary mission is to continuously carry heat away from the reactor core, ensuring that all components operate within their safe temperature limits. Failure to do so could lead to a cascade of problems, which is why scientists and engineers are always looking for new ways to make these cooling systems even better. The challenge is that this isn't just a simple matter of pumping water past something hot. The process has to be perfectly controlled and understood. Every single part of the reactor core needs to be cooled effectively, without any weak spots or areas where heat could unexpectedly build up. This quest for perfect cooling has driven decades of research, pushing the boundaries of materials science and fluid dynamics. We're talking about managing extreme temperatures and pressures with pinpoint accuracy, all while dealing with the complexities of a nuclear environment. It's a high-stakes puzzle where the pieces include water, metal, and the fundamental forces of the universe. So when we look at a nuclear power plant, we should see more than just a source of electricity. We should see a triumph of thermal management. The silent, steady work of the cooling system is what makes everything else possible. It's the unsung hero that guarantees the safe and reliable operation of the entire facility. As we push for even more powerful and efficient reactors in the future, the need for innovative cooling technologies becomes more critical than ever. The journey to improve nuclear energy is, in many ways, a journey to find smarter and more effective ways to handle the heat, ensuring a safe and sustainable energy source for generations to come. To understand how we can improve cooling, let's take a peek inside the most common type of nuclear reactor, the Pressurized Water Reactor, or PWR. Imagine a giant, super strong steel vessel which holds the reactor core. This core is made up of thousands of long, slender metal tubes called fuel rods. These rods are bundled together, and they're where the magic happens. They are filled with small pellets of uranium fuel, and it's within these pellets that nuclear fission takes place, releasing all that amazing heat. This entire assembly is submerged in water, which acts as both a coolant to carry away the heat and a moderator to help control the nuclear reaction itself. It's an incredibly neat and contained system. This water is kept under very high pressure. That's the pressurized part of the name. Keeping the water under such immense pressure allows it to be heated to extremely high temperatures, well over 300 degrees Celsius, without it ever boiling. This superheated water is then pumped through a closed loop of pipes into a device called a steam generator. Here, the heat from the reactor water is transferred to a separate secondary loop of water. This second loop of water, which is at a lower pressure, instantly flashes into high-pressure steam. This steam is then channeled out to spin the turbines that generate electricity, completing the power production cycle. Let's zoom in on those fuel rods, because they are the heart of the heat transfer process. Each rod is a meticulously engineered component. On the inside, you have the uranium fuel pellets, which are like tiny ceramic cylinders stacked on top of one another. The heat generated by fission has to travel from the center of these pellets outwards. It passes through the pellet itself and then through a protective metal casing called cladding. This cladding, usually made of a zirconium alloy, is what separates the radioactive fuel from the coolant water flowing outside. Its job is to contain the fuel securely while allowing heat to pass through it as efficiently as possible. The efficiency of this heat transfer from the cladding surface to the surrounding water is absolutely vital. The faster we can pull heat away from the fuel rods, the cooler they stay. This not only improves the overall efficiency of the reactor, allowing it to produce more power, but it is also a massive factor in its safety. If heat isn't removed quickly enough, the temperature of the cladding can rise, potentially weakening the metal. Therefore, ensuring that the coolant water makes good, consistent contact with the entire surface of every single fuel rod is one of the most fundamental challenges in reactor design. You might think that making the fuel rod cladding perfectly smooth would be the best way to let water flow past it. It seems logical, right? A smooth surface should create less resistance. However, in the world of fluid dynamics, things aren't always so simple. When water flows past a smooth heated tube, a very thin layer of water right next to the surface, known as the boundary layer, tends to move more slowly than the rest of the flow. This sluggish layer acts like a small insulating blanket, making it harder for heat to transfer from the metal cladding into the bulk of the coolant. It's a tiny barrier, but in a nuclear reactor, every bit of thermal resistance matters. This boundary layer effect can lead to a serious problem: the formation of hotspots. Because the heat isn't being carried away uniformly, some areas on the fuel rod surface can become significantly hotter than others. These localized hotspots are a major concern for reactor safety. If a spot on the cladding gets too hot, it could weaken the material, increasing the risk of a breach. Furthermore, in certain conditions, the water in that slow-moving boundary layer can even start to boil, forming a layer of steam bubbles on the surface. This is known as a departure from nucleate boiling, and it's very bad news, as steam is a much poorer conductor of heat than liquid water, causing temperatures to spike dramatically. The challenge is further complicated by the fact that the flow of coolant through the tightly packed fuel rod bundles isn't perfectly uniform. The water tends to flow in straight, parallel lines, a condition known as laminar flow. This means there isn't much mixing between the hot water near the rods and the cooler water in the center of the channels between them. Without good mixing, the coolant can't do its job as effectively. We want the flow to be turbulent, with swirls and eddies that constantly churn the water, bringing cooler fluid to the rod surface and whisking the hot fluid away. It's this turbulent mixing that dramatically enhances heat transfer, so the smooth, elegant design of traditional fuel rods, while simple, presents a fundamental thermal hydraulic challenge. It creates the conditions for poor heat transfer, inefficient mixing, and the potential for dangerous hotspots. For decades, engineers have tried to overcome this by increasing the overall flow rate of the coolant, essentially trying to blast the heat away with sheer force. But this requires more powerful pumps, which consume more energy and put more strain on the system. It became clear that a smarter, more elegant solution was needed, one that would change the very nature of the flow itself, right at the surface of the rod. What if, instead of fighting the fluid, we could trick it into behaving the way we want? This is the brilliant idea behind the latest research into fuel rod design. Scientists took inspiration from a surprising place: a golf ball. A golf ball has dimples on its surface not for looks, but because they make it fly farther. The dimples create tiny pockets of turbulence that help the ball cut through the air with less drag. Researchers wondered if a similar principle could be applied to nuclear fuel rods. By adding a pattern of dimples to the surface of the cladding, could they disrupt that insulating boundary layer and encourage the turbulent mixing that is so crucial for cooling? To test this idea, without building a whole new reactor, scientists turned to the amazing world of Computational Fluid Dynamics, or CFD. CFD is like having a virtual laboratory inside a supercomputer. Researchers create a highly detailed, three-dimensional digital model of the fuel rod and the channel it sits in. This digital space is then broken down into millions or even billions of tiny cells, forming what we call a mesh. The computer then uses complex equations to simulate how the coolant water would flow through this mesh, cell by cell. It can calculate the velocity, pressure, and temperature of the water at every single point in the model, giving us an incredibly detailed picture of what's happening. Using these powerful CFD simulations, researchers compared the performance of a traditional smooth rod with a new dimpled rod. The results were astounding. The simulations showed that the dimples worked exactly as hoped. As the coolant flows over the dimpled surface, it creates tiny, swirling vortices. These little whirlpools of water act like microscopic agitators, breaking up the slow-moving boundary layer and promoting vigorous mixing. The hot water at the rod surface is immediately swept away and replaced with cooler water from the main flow. This constant churning dramatically improves the rate of heat transfer. The key metric scientists look at is the Nusselt number, which is a measure of how effective the heat transfer is. The CFD results showed that the dimpled rods had a significantly higher Nusselt number compared to the smooth ones, meaning they were much better at getting rid of heat. This directly translated to lower cladding surface temperatures, reducing the risk of hotspots and increasing the overall safety margin of the reactor. The dimples were successfully engineering a more turbulent, and therefore a much cooler, environment right where it was needed most. It was a simple change with a massive impact. Of course, in engineering, there's no such thing as a free lunch. While the dimples were fantastic at improving cooling, they also had a side effect. The same turbulence that enhanced heat transfer also created a bit more resistance to the flow, leading to a slightly higher pressure drop across the fuel rod. This means the main coolant pumps would have to work a little harder to push the same amount of water through the core. The challenge then was to find the perfect balance, a dimple design that gave the biggest cooling boost for the smallest pressure penalty. To solve this optimization puzzle, researchers employed another clever computational tool: genetic algorithms. A genetic algorithm is a search method inspired by Charles Darwin's theory of natural selection. The computer generates hundreds of different dimple designs with varying depths, diameters, and spacing. It then tests each one using the CFD model to see how well it performs in terms of both heat transfer and pressure drop. The fittest designs, those with the best balance, are then bred together to create a new generation of even better designs. This process is repeated over and over, allowing the computer to rapidly evolve the optimal dimple geometry without a human having to guess. This process found a sweet spot that provided a major cooling improvement with only a minor increase in pressure drop. With a promising design in hand, the next step was to ensure the dimpled rods were still structurally sound. The cladding on a fuel rod has to withstand immense pressure, high temperatures, and a harsh radiation environment for years. Would adding dimples create weak points? To answer this, engineers used another type of computer simulation called finite element analysis, or FEA. This analysis models the physical stresses within the cladding material itself. The results confirmed that, with the optimized design, the dimpled cladding was just as strong and reliable as a traditional smooth rod, ensuring that this new innovation wouldn't compromise the structural integrity of the fuel assembly. The implications of this research are incredibly exciting for the future of nuclear energy. By significantly improving heat transfer, dimpled fuel rods could allow future reactors to operate more safely and efficiently. This could mean running reactors at higher power levels to generate more electricity from the same amount of fuel, a concept known as a power up rate. Alternatively, it could allow for the design of smaller, more compact reactors without sacrificing safety. As we look towards advanced and next-generation reactor designs, like small modular reactors, innovations like this that enhance inherent safety features will be absolutely essential, paving the way for a new era of clean, reliable, and even safer nuclear power.